Okay, so up to this point, we got all this information in our heads about this DC motor, and we've looked at different configurations for it. But one thing we haven't done is we haven't connected a load to it. And what good is a motor without a load connected to it? So that's what we're going to do in section 5.7 called shunt motor under a load. So we're going to take that same motor that we were looking at in 5.6, and we're going to connect a load to it, and we're going to see all the things that happen when that occurs and how the motor reacts to that. And we have this wonderful base now, knowledge of equations and all from the earlier parts, and we're going to apply that to this situation where we're putting this motor under a load. We're putting it to work. That's why we have this thing, right? We want this motor to do something. So we connect a load to it, and it gets ready. And now I'm going to back up on you a little bit. I've failed to talk to you about something that's very important, and it has to do with these torque speed curves. And I brought it up in the last section, but I didn't do anything or talk about it. So let me pull this back up and let's look at this. It's very important. Okay, so we talked a lot about, the schematic over here, and I mentioned this, these curves, but I didn't talk to them in much detail. And so really important. A couple of things I'll point out to you as I make this a little easier to read. This is a curve that reflects the characteristics of a shunt motor with the field in parallel with the armature. And so what we're doing, first off, notice this is in per units, okay? And when we first talked about per units, I was telling you how important it is and how that is the sort of the standard when you're working with electrical machines is these per unit values. And we're going to start to see that incorporated into these characteristic curves. Okay, now usually at 1 per unit of whatever it is that you're measuring, those are rated, RATED conditions. And so, those are sort of important places for us. And we could see those 1 per units, here, and we'll talk about what all that means in just a second. But these curves are twofold. One is a curve that gives us the speed versus the torque. Okay, so here we've got speed versus torque, and the other one we've got current versus torque. All right, and so we're actually graphing two curves together on the same axis. And let's look at this one first, the torque versus current. Very obvious. We know from old math days that this is an mx, y equals mx plus b linear relationship type of a curve. And so we're seeing that there. So we can clearly say that the change in current gives us a direct proportional change in torque. More current, more torque. Basic, fundamental thing we want to make sure that we cement in our machine's knowledge. The other thing that we'll look at is the torque versus speed situation. And, it's not as quite maybe as obvious as the torque versus current, but notice, and we'll revisit this later in a problem, but notice how almost vertical that line is. Okay, so what does that tell me? What does that tell me when there's not much variation on a particular curve? Well, what that tells me is that for this situation, there's not much variance, right, between the torque and the speed. And so that's maybe something else we want to file away and consider when we're thinking about a shunt connected motor. All right, but for the time being, let's just make sure that we can read these values and we understand, we've got two curves, it's in per units, it's torque versus speed, it's torque versus current, and so we're working off of that. Okay, now let's go over here And I'm gonna, oops, bring this back to here. And I'm gonna clear out some stuff so that we can explore this section 5.7. And I will tell you, after you watch this section 5.7, there'll be another quiz. There's two quizzes, right? One from 5.0 to 5.2, and then the second quiz picks up and goes 5.3 through 5.7. So, you know, first off, here's a shunt DC motor, and what we're looking at it right now is it's running at no load, okay? Now, if we come out here somewhere and connect a load to this motor, I'm going to just come out here and do this and put a load out here, okay? And when I connect a load to this motor, what happens is if the mechanical load is applied to the shaft, there's the small no load current is not enough to provide the torque, so the motor begins to slow down, okay? Now, this causes the CEMF to diminish. When the CEMF diminishes, the current increases, okay? Because that difference between source and armature voltage increases. So when that happens, we get a higher current. When we get a higher current, we get a higher torque. Then once we get this higher torque, the armature accelerates again, and the torque developed by the motor, and it will continue to accelerate until the torque developed by the motor is almost exactly equal to that of the mechanical load. Then at that point, the speed will level off, okay? And then he says to sum up, as the load increases, the current rises and the speed drops, okay? And so in response to this, you know, the torque increases, the speed increases until it matches and so forth. And that's how this thing motor reacts. Now, the speed of this shunt motor, it stays pretty much constant from no load to full load. And that's what we're seeing in this particular curve here. In small motors, it only drops 10 to 15% when fully loaded. Okay, so you got the motor, say it's running at no load, and then I couple a load to it, and the speed will only vary 10 to 15% from no load to full load. And then in big machines, that drop is even less. And actually, we'll talk about what is a big machine, what is a small machine in material that comes up later. But anyway, so the adjusting the field rheostat can, and of course, be kept absolutely constant as the load changes. So we could monitor the load, and based on what that load is, we could change the field, and we could react to these load changes. And that's what control systems do. It's not me manually sitting there watching this stuff. You know, it's all electronically controlled and monitored, and then we can adjust to that. And I guess the last thing here is back to this curve, and I'm going to blow this up one more time here and read this last paragraph with us. Typical torque, speed, and torque current characteristics are given in 5.8b. The speed, torque, and current are given in per unit values. The torque is directly proportional to the armature current. Furthermore, the speed changes only from 1.1 per unit here, not there, but here, okay? 1.1 per unit to about 0.9 per unit here. That's kind of what that's trying to show us. And as the torque increases, from 0 to 2, okay? So we only move this much, you know, on the curve, you know, in relation to this 1.1 per units of speed to about 0.9 with a from a 0 to 2 increase in torque. All right, so what does that mean? Let's put it in just a plain English, as in a shunt configured DC motor, there is not much variance with the torque from full load to no load, right? The speed doesn't change very much. What we're saying again, 10 to 15%, even less for larger motors. All right, I better stop here, and then I'll make one more video, which will be example 5.4, and we'll explore some of these things that we have talked about up to this point.